So at this week's AI seminar, we're joined by Assistant Professor Yizhe Zhu, Assistant Professor in USC's Math Department. He's working on probability, combinatorics, and data science. And before USC, he was a visiting assistant professor at UC Irvine and a postdoc at the Simons Law for Mathematical Science Institute at Berkeley. He earned his PhD in math from UC San Diego. I just learned he previously was at Washington. Yeah. And he's going to be talking to us about some of his work on generating differentially private. Speak to us about it.
Thank you, Eric, for the introduction. It's my pleasure to be here and welcome to my talk. Today I will talk about a combination of two concepts. One is differential privacy, another concept is synthetic data. The question mark was not to me, but yeah, it's a question to ask. What is differentially private synthetic data? Okay, so let me start with acknowledging my collaborator. So Yiyun He is formerly a PhD student of Professor Roman Vershynin. He's now a postdoc at UC San Diego. And this is also joint work with Professor Strohmer at Davis and Professor Roman Vershynin. Okay, so right now we are not, we're very familiar with synthetic data nowadays because of this ChatGPT and many generative model. You can easily to get synthetic data from generators. And this is a picture I borrowed from a consulting company's prediction that they believe, I think this prediction was made around 2022. They predict around 2030, the number of synthetic data will be much more than real data set. But we're now at 2025, you can see it's already happening that the number of synthetic data is way more than real data, because you can generate by using those ChatGPT portal, or you can just adding some noise to your data. There are many ways to generate synthetic data. So it is a very broad concept. Compared to real data, there's some obvious benefits. For example, it's easy to get. Also, you can make some privacy guarantee compared to the real data. How do we really quantify that? That's the key question. So, for example, synthetic data can be used to train like an autopilot system in an EV, because you can simulate some extreme situations, like likely to have a car accident. In reality, it's hard to acquire those real data, but you can train your machine learning system on the autopilot model with synthetic data. Also, another very important application is when you look at healthcare data, because the medical data are very sensitive to use. But if we want to train a machine learning model based on medical record, it's better to use synthetic data instead of the real data, so that we still get some statistical guarantee of your machine learning model. Okay. And another big area of synthetic data is for financial data. For the same reason, it's very sensitive to require real data from users' data set, but you can somehow manipulate a synthetic data and use that as your training samples. Okay, so one thing we need to worry about is synthetic data does not mean the data are private already. For example, I can create a facial recognition system based on some faces, and I can twist your eyes or mouth or ears, some features of your face, but still, by looking at those training sets, you will be able to identify who are inside this data set, right? So we need a way to quantify what is privacy and what is the utility of those synthetic data set. And this is the topic of today. We want to build a mathematical foundation, a principle to generate synthetic data. Okay, so one way to quantify the privacy of synthetic data is to use this commonly used notion, differential private. privacy. The general idea is you look at an output of a randomized algorithm. By looking at the output, you cannot tell whether an individual data is involved in this computation or not. This is the high level idea. So this is not about a property of the data set. Differential privacy is a property of a randomized algorithm. So the formal definition is following. We consider an algorithm A that takes the input data, a set of endpoints, to another domain. Right? This algorithm is said to be epsilon differential privacy if you take two adjacent data sets. Think about those two data sets, D and D prime, they differ by one user. So one user is involved in D, but not in D prime. Or you change one user A to another user B in D prime. And we look at the output of this algorithm, that's this A of D, this output. Let's make it a randomized output. So this is where you can talk about differential privacy. This algorithm must be randomized. And the randomized output will be a random variable. It has its own distribution. So this picture says, by looking at the distribution of output of D and the distribution of the output of D prime, those distributions are close to each other. So you cannot distinguish the output distribution by looking at D or D prime. Okay, this is the definition of differential privacy. And this quantifier is this epsilon, which basically quantify the ratio of any point in this density. So by looking at the density of any point, the output of D and D prime, they're bounded above and below by this e to the epsilon. So there has been a quite commonly used framework to rigorously prove privacy, and it has already been adopted in US census and many companies' products like Google, Amazon, Apple. They already use this framework to train their model to satisfy the differential privacy. Okay, so this is how we quantify privacy. So let me just give you a brief idea of how do you guarantee differential privacy by creating a randomized algorithm. The simplest framework is to just add some noise to the output. This can make your algorithm private. So the simplest example we can imagine is let's compute the mean of n data points. Think about it as like computing the average salary of n users. This, if we just do it without randomness, we'll just take the average of n value. But by making a randomized algorithm, you just add a Laplace random noise. Okay, this Laplace random noise satisfies a exponential tail, and it will help you to guarantee this definition of differential privacy, because if we look at the ratio of the output for data set X and X prime, where X prime differ by one element, you can compute the density ratio, and it's upper bounded by e to the epsilon. Okay. So it's easy to check this algorithm satisfies differential privacy. So this is the general strategy for many differential private algorithms. You have a way to compute some quantity, and I add a little bit noise to make this algorithm random, and it satisfies this definition of DP. Okay, so one thing we can quantify is how much error I will make. By introducing this randomness in expectation, this new output A of X compared to the true mean is of the order 1 over epsilon n. Okay. So this will give you an idea how can we make things private and useful. First of all, if n is large, that means there are many data involved in this computation, this accuracy will be better. Right? And epsilon will also be a trade-off, right? For epsilon being small, it will be more private. Think about it. If epsilon is 0, that means the output distribution is the same for two data sets. Then I have no way to tell which data set is used. But if epsilon is very big, you can imagine there's quite a bit deviation between those two outputs. So that creates some way to detect this user information. So epsilon is a quantifier of privacy. If epsilon is small, it's more private, but then the error will blow up, right? If epsilon is small. So there's a trade-off between privacy and accuracy. You can imagine this is a classical way to arrive differential privacy, and we can extend this to many other tasks. For example, private linear query, meaning I want to compute a linear function of the data, and I can just add the noise to this. And you can do high dimensional mean and covariance estimation. And in many optimization procedural, the commonly used method is stochastic gradient descent, and you can inject noise in the stochastic gradient descent to guarantee the empirical risk minimization is private. And also private SVD, meaning in many numerical algorithms, you have to do the singular value decomposition, and you can add noise to this SVD procedure to create a private output for many numerical algorithms. Okay. Another thing I want to mention is if we want to inject noise instead of Laplace, we can think about another common choice is Gaussian noise. Gaussian noise will not satisfy this epsilon differential privacy, but you need to introduce another parameter delta, which quantify the privacy in this way. The probability of AD in the set is upper bounded by e to the epsilon of AD prime, but with the other additional quantifier delta. Okay, so we think about delta to be a small number, and that is a more relaxed version of differential privacy. If delta equals 0, it's the pure differential privacy we already introduced. Okay, so this is a general idea of differentially private computation, and there's some limitation of this, right? I need to tell you what kind of computation I want to make. So I'll say, I'm gonna do singular value decomposition of the matrix and say, okay, I will add the noise. If I want to do mean estimation, I need to do another way to add the noise. So if I do several multitask on the same data set, I need to pay this privacy cost many times. So it's specific, and I need to have certain expert knowledge to design my way to inject the noise to guarantee privacy.
It's back.
So this way, we always output the private quantity by adding noise tailored to the task. There's another way to think about it. Is it possible that I just construct a private synthetic data once and for all? Then for many other tasks you want to perform, you just apply it on the synthetic data set itself. There is some post-processing theorem to says if you already have a differentially private data set, and any computation on this data set will be private afterwards. So it guarantees privacy of many or all downstream tasks. But the issue is still, what is the utility? Right? I can say this is a private data, and what is the utility? Okay. So what is our goal? We want to output a private synthetic data that's useful for a class of downstream tasks. First of all, it must be globally similar. Otherwise, I destroy the statistical property of the true data set. Still, it must be locally different. It protects individual information. Okay. So what is our mathematical framework for private synthetic data? You can still think about generating synthetic data as an algorithm. The input is my original data set X, and I want to output another data set Y. Here, X, Y might have different size. Since I care about statistical behavior, they can have different size. So one thing we want to guarantee is privacy, meaning this generation algorithm, right, from data set X, data set Y, is a epsilon differential private algorithm. And we want to have accuracy such that Y is statistically similar to X, meaning if you perform some machine learning task on X, the output should be similar to Y. Okay. Also, we care about efficiency. So this algorithm should run in polynomial time. For example, the downstream tasks you can think about could be like clustering, classification, or regression. There are many basic machine learning tasks you want to ask. So there are some previous work on this framework, but we will introduce a method that's satisfying 1, 2, 3 property altogether. Okay, so here's the key quantity we want to introduce. How do we quantify the utility of the synthetic data? There's one important point of view is to view the data set as a probability measure. In this way, we can compare them in a compact way and a very general way. So how do we think about this? If I have original data set X, I can create a probability measure, which means with probability 1 over n, I will take x1. With probability 1 over n, I will take x2, and so on. So this is a uniform measure on endpoint. This is my starting measure, x. And the output, I can also interpret it as a measure. It's another measure, y, that put 1 over m chance on each data point. Okay. If I have two measures, I can compare how close those two measures are. Okay. And this will connect to another theory called optimum transport, where I can define the distance between different probability measures and talk about how to quantify this distance, right? So especially we're looking at one Wasserstein distance, which essentially measure how much effort you need to move a collection of data point to another data point. How on average, what is the distance you need to move points? Okay, so if we are having the same number of samples, endpoint x, endpoint y, this is the average distance you need to move to match those two distributions. Okay, it has a nice duality formulation. Says if I look at the Wasserstein distance between x and y, this can be written as the supremum over all Lipschitz function applied to x and y. Okay, so this will be useful to interpret it as a utility result for a machine learning task, because f could be the function that you care about, and f d mu x minus f d mu y is the difference of the output, right? The difference when you apply the function to this. So essentially, the small Wasserstein distance between the true data set and the synthetic data will imply the new data set y will be useful for any Lipschitz task. So if the function applied to those synthetic data is a Lipschitz function, you will have some guarantees. For example, regression, clustering, classification, and we also know that in many cases, neural network is a Lipschitz function, so you can quantify the output of the neural network by looking at the Wasserstein distance. This is not the only distance you can care about between two probability measure. You can also look at L1 distance or smooth function applied to this data measure. Instead of Lipschitz, I can talk about supremum over smooth function, or you can look at more variation of Wasserstein distance, like a sliced Wasserstein distance, by looking at one-dimensional projection of the measure. It's an easier measure to look at. Okay, so let me give our first result, which is a efficient way to compute this output synthetic data y that satisfy first is differentially private. Second, the Wasserstein distance has a good utility guarantee. Third, it runs in polynomial time. So in fact, I will present two algorithms, and I will mention that many other follow-up work built on those algorithms, and they already apply to different settings. So both methods will be interesting to look at. First of all, this error rate is if essentially tight, it matched a n to the minus 1 over d bound in the previous work. So I will give you an intuition why this n to the minus d will appear. Okay. Also, we improve some polylog factor in our paper. So where is the n to the minus 1 over d appear? So imagine I have endpoint that's uniformly distributed on this d-dimensional hypercube. The average spacing of points is of order n to the minus 1 over d. Okay. So if I want to create a synthetic data from original data set, if the data are uniformly distributed, I need to make those points move. Right? Otherwise, if they just have a tiny bit perturbation, I can say, okay, nothing is moved, so I can identify A with A, B with B. Right? So in order to make them move, I need to make every point swap identity so that you get confused which point is the original one. If all the points need to swap identity, then they need to move at least n to the minus 1 over d. Right? They need to get out of those neighborhood radius to swap identity. So this is essentially the lower bound we get. So this implies this our rate is minimax optimum in the worst case. So what is the idea for creating a synthetic data? Now we already make it abstract. I think about x is a d-dimensional vector in the hypercube, but this can also be a tabular data, and you just map it into the 0-1 interval. So we make it more general. You can also think about it in an arbitrary metric space, but the hypercube is a good example to think about. So we first make a binary tree partition of this hypercube. So how do we do the partition? You just always split every cube by half, and by half, cut it into small pieces. So the number of sub-intervals will be, you can encode it by a binary tree. In the first partition will have 2 intervals, and then so on, and 4 intervals, and it grows exponentially. And you just add noise to the count of each subregion. My data points live in the hypercube, and each certain region, I know how many data points are there, and I perturb the count. Okay. The key thing is you don't perturb the location, you perturb the count. So by perturbing the count, we add some Laplace noise. Right? And to make this final count be an integer, we can add some Laplace noise with integer value. This can be guaranteed. And afterwards, there are some issues. If I have a region where originally no point was there, and I perturbed by some Laplace noise, the number of points could be negative, right? That's one issue. Another issue is if I perturb this region, or my original total point is n, but those two regions, the sum does not add up to n. So we have to correct this number of points to make it consistent. How do you do that? You do from a top to bottom by correcting them so that this region 0 and region 1 add up to n, and 0, 0, 0, 1, the number of points add up to this region, so we can make it consistency. Okay? By making the consistency, it actually makes the utility better. And afterwards, we already get some private count in certain region, each region. And I just pick an arbitrary center point in each region and move all the point in that point. Okay, is the idea clear? So we perturb the count in each subregion by adding this noise, and then we make it consistent. Afterwards, I know the private count in each region. I just pick an arbitrary point in that small region and move the point to that in the bottom level. Okay.
I think the last step is a little unclear for me still. Like you have an existing, like, let's say, endpoints in that region. You're sampling from those endpoints.
Yeah.
And then
so the count becomes private already.
Yeah.
But I also need to make the location independent from the original data. So I just aggregate.
You're aggregating real points.
Real points.
And you're taking the like centroid.
Yeah. Something arbitrary.
Oh,
you want to make it independent of the data.
Oh, okay. Like a random.
But this only sacrifices a tiny bit of the utility.
Because you're
I'm not moving it very very far. I'm looking at the bottom level. Okay, so you will take this level like logarithmic level.
Okay.
By doing that, essentially we get the utility we have. Okay. So in fact, this algorithm is quite intuitive. It has been used as this top-down algorithm in 2020 census. So you can think about if you want to do a survey, you want to perturb your survey result at the county level and city level and street level. But if you perturb it, the survey might not be consistent. So you need to correct it from top to bottom. But we provide a theoretical guarantee for this. And in fact, this is also related to some measure quantization in the theory of optimal transportation. Okay.
You have, I mean, if the data is very sparse, does that change anything in this analysis? Because if you have zero.
Very good question. So if the data is very sparse, this might be overshooting, right? Because there are many regions I have zero count, and I just get the I perturb the node, I perturb the count, and I need to come back to zero. So so that's why I say our bound is the optimal in the worst case if all the data are uniform distributed. If your data has some skewness, like sparsity, you can do better. There are follow-up work based on our method that you can do better. For example, if you see a region that's zero, you can just give up on those regions. I don't perturb that. So that will help to make the utility better and adapt it to your data set. Okay. And there's another algorithm that has been generalized to other settings, which is also quite intuitive. Instead of looking at this.
Can I answer this? So I mean, this depends on the, if you go back to the previous slide.
Yeah.
So this depends on the dimensionality. No, I mean, so as the dimension gets bigger, like with, so you are doing images with millions of pixels and stuff like that. So how does this scale? I mean, is there a limit with the practical
Yes,
limitations?
very good point. There, now I should mention, first of all, if you look at this error rate, this D cannot be very big with N. If D is like order log N, this is already order 1. So the dimension should be a small. You should think about D as a fixed number. Okay, this is one thing. This is a limitation of this. I'll talk about how to address that. And also, there are hardness results in cryptography saying if you want to create D-dimensional synthetic data that has a good utility in the sense that like 2-dimensional margins are kept, you have to run in exponential D time. So there is a curse of dimensionality for synthetic data from hardness result in theoretical computer science. Essentially, you can only hope for good synthetic data with good utility guarantee in low dimension, in the worst case. If your data is in some low dimensional manifold embedded in the high dimensional data, it might be doable. But in the worst case, it's impossible.
So what would you say would be a reasonable dimension? I mean, we're talking about 100 dimensions, 10 dimensions?
Yeah, if your D is like a 10 and N is much bigger than D, then this is still okay.
Okay, thank you.
Okay, so another way to generate the synthetic data in this hypercube, we have a simpler method which only works in D dimension when D greater equal to 2. But the idea is you just do a equal partition of the region into small region. And a similar idea, you look at the count in each region and you perturb it to adding those Laplace noise. Afterwards, this will be a measure, but with some negative counts. Right? So if I look at the measure of this distribution, it will be a signed measure. In certain region, it has negative mass. So a simple way to correct it is I can project this measure into a probability measure by looking at the closest probability measure to this signed measure. And this can be done via a linear programming step, which is polynomial in N. And this linear programming, why is it possible? Because I can make sure all my probability measure is supported on certain single point in each region. So I only care about the value of the probability measure in a certain location. And this will make it a polynomial type. Afterwards, you can just generate synthetic data from this new measure. Okay. And in this way, we get a different result, which match the previous method when dimension d is greater than or equal to 2 up to log factor. But in one dimension, this is not the best rate. Okay. And in the analysis, we discover a certain complexity measure that's useful for an analysis of differentially private algorithm, which is related to, if you heard about this Gaussian or Rademacher complexity when you look at pack learning theory or empirical risk minimization. And for differential privacy purpose, how we want to measure what is the class of function, how do they respond to the noise. This will be measured by this Laplace complexity, which says if I add Laplacian noise, what is the expectation of this supremum of the process? In this proof, essentially, it works by bounding this Laplace complexity for all Lipschitz functions. So we measure this difference of the Wasserstein distance by bounding the Laplace complexity, and we work out the case for d-dimensional hypercube. The Laplace complexity match essentially the Wasserstein distance rate, and after other calculation, you can translate this Laplace complexity result to the Wasserstein distance rate. So this gives you a general framework, not just for Lipschitz function. If I ask you a different function class f, maybe smooth function, polynomial function, you can just work out the Laplace complexity of that function class, and you can adapt your analysis to a different class. Okay, so I already mentioned that n to the minus 1 over d is the rate we prove, but if d is large, this error rate is not useful. Right? Only when d is below log n, this is vanishing. And essentially, this is a common situation when you do high-dimensional density estimation or in Wasserstein distance. If the dimension is high, you need to have many sample points to learn a distribution in high dimension. Okay, so we can make additional assumptions of the original data set to break the curse of dimensionality. For example, in our follow-up work, we assume your data lies on a d-dimensional affine subspace. So imagine this is a hypercube and your data lies in this is like a one-dimensional or two-dimensional space, but it's unknown, right? So I know, I don't know where the affine subspace is, okay? And we can use this data structure to improve the error rate to n to the minus 1 over d prime, where d prime is the intrinsic dimension of the data. So that will help you to deal with high dimensionality. If you know some additional structure of the data, you can improve the rate. Okay. The general idea is to combine PCA, which is a principal component analysis, a dimensional reduction procedure, and adapt the private measure mechanism we introduced before. So essentially, the general idea is you have a collection of data, and I want to project my data on this subspace, and I do my count perturbation in that affine subspace. Okay. So I want to mention there are other results where they assume data from a d-dimensional unknown manifold, but the algorithm is not efficient. In our case, it's based on PCA, so linear algebra tool is very efficient. Okay, so this is our result. If you have a d prime, that's the quantified intrinsic dimension, and I can compute a differential private data y such that the Wasserstein distance is bounded by essentially 3 terms. The first term is if I do a singular value decomposition, I throw away the small singular values of the centered covariance matrix, what is the cost of projecting the data to low d prime dimension? This is the singular value decomposition cost. And there's another term that's essentially to make the singular value decomposition private, I need to pay a cost. And the third term is when we want to perturb the number of data points on that subspace. You pay a d prime dimensional error in the Wasserstein distance like before. Okay. So this is adaptive to your data set. If your x is not exactly d prime dimensional, and this term will not be 0. But if your data set it is really d prime dimensional, then the singular value after d prime is all 0. So you don't have this SVD error. I'll just briefly mention that. Yeah. So I'll just skip the detail. Essentially, we just provide a private covariance matrix by adding noise to the central covariance matrix, and you do a SVD procedure, and then you project your data on this d-dimensional subspace, then perturb the count in those subspace. Okay, so this is the way we get the break the curse of dimensionality. And technical tool is we want to quantify when we add a noise, what is the error you get from the singular value decomposition. Then there's a useful lemma. We prove that does not rely on Davis-Cahan theorem or spectral gap condition of your data matrix. Okay, I'll be quick on that part. So another generalization I want to mention is how do we make synthetic data in an online fashion? So you can think about, there are many data that arrive in a streaming fashion, like the COVID data set or Uber location data that you get data one by one. But our goal is at every time step t, I need to give you a synthetic data set y that resemble my point x1, x2 up to x2t. So at time t, I give you a yt. At times t plus 1, a new data arrive. And I want to update my synthetic data set to get a new synthetic data set. But there's a caveat. I cannot just create a new synthetic data. Imagine I already have t point and a t plus 1 person arrive. If I just give you a new synthetic data, you know this must identity, you can identify the new y with the x, new x, right? So instead, at every time t, we create a new data set of size t. So day 1, I have new data set of size 1. Day 2, I have data set of size 2. You already observe 3 synthetic data. So the new data set, they're not overlapping with each other. This is a way to guarantee privacy. Otherwise, I can just identify the new arrivals. Okay. But you can imagine this is more challenging because at time t, I have access to y1, y2, y3 up to yt. So I have way more data than the offline case. By looking at synthetic data, you might think, okay, it will be easier to detect any person involved in this original data set. But our result says we can create an algorithm that output the synthetic data for any t. Okay. You can have infinite amount of data, and I can guarantee at every t, this Wasserstein distance is small. Compared to the previous result, we only sacrifice a polylog factor. And so this the cost for online data is only polylog in this study. Okay. And this is based on some protocol that people studied called a binary tree mechanism, which keep track of a online count of counting data. Okay, so this is based on another model where you have a collection of data set that's 0 or 1. You arrive one by one, so x1, 2 to xt. At any time t, you want to output a private count st of the partial sum. Every time you need to output a partial sum. How can I guarantee that the error of the partial sum is slowly growing, while I keep differential private for all the partial sum. So this is a protocol called the continuous release model, and there's a classical binary mechanism where you can create a tree structure to keep track of those partial sum and add noise to the nodes of the tree. Okay? And we can kind of borrow this data structure and adapt it to our case where all the data are not 0, 1, but a vector in the dimensional space. Okay, this is essentially, yeah.
Is there any expectation of like the stability of the distribution over time?
This case is the worst case bound you can prove. Like, I don't know whether X is 0. What's the distribution of 0, 1?
Well, let's say you're Uber and you're trying to predict where people will go, and the Olympics happen. So now everyone is going to these stadiums that they weren't going to before, right? So there's been this sort of, event which changes the distribution prior to the event. And so I'm just trying to kind of square that with what's going here, where, given that change in distribution at a kind of based on this event, what does that mean?
So you want to say there's a distribution shift,
Right.
of 0 or 1s.
Yeah.
Yes. However, whether this is the private information or public information.
I imagine as you're doing this, right? So there's some change in the signal and some change in the kind of noise that you're using for privacy. And as long as, both occur, then they might balance, at similar magnitude. But if the signal changes a lot,
I think in this case, you can guarantee privacy while you still keep this event information.
Mhm. Yeah.
This is the utility you want to keep.
Okay.
So let me conclude with the summary of the result. So we can generate differential private synthetic data by keeping a guarantee of high accuracy with respect to Wasserstein distance. And this utility guarantee is good for all Lipschitz queries, and this query does not need to be predefined. So this is our mathematical framework to define the privacy and utility. If we have a low dimensional data from high dimensional data set, we can improve the accuracy rate. And we can have a adaptation to streaming data in online fashion, which only sacrifices the log factor utility loss. I want to mention there are many follow-up work based on our either proof techniques or the formulation of this utility. There are results of where you can reduce the memory cost and make your error rate adapted to the sparsity of the data. There are analysis of a more practical algorithm called private evolution that's based on our analysis, and synthetic data generation based on our framework. Also, some downstream tasks based on the private measure algorithm. For example, you can compute the Wasserstein barrier center in a differential private way. This is based on some of our technique. And how do you generate the histogram of the data with differential privacy guarantee? And there are some future directions I'm interested. First thing is this worst case bound in the 1 Wasserstein distance is still very pessimistic. It's n to the minus 1 over d. But in many situations, we don't care about the worst Lipschitz function applied to the data set. Maybe I care about some very nice function, the polynomial or smooth function. And this should be improved if I restrict myself to a different function class. Okay. And this is an open question. If I give you a nice function class, can you create an algorithm that makes the output nice in this measurement, like a universal algorithm adapted to the query? Another thing is, if I want to have a low dimension nonlinear manifold, what can we do? Then the linear algebra tool is not valid. I need to deal with this nonlinearity in manifold setting. And there are some work, but that's not very efficient. And the third big topic, I would say, there are many specific architecture to generate synthetic data using DP generative adversary network or differentially private diffusion model or just general neural network architectures, you can guarantee privacy easily by saying I'm injecting noise in the optimization procedure. But currently, there's no utility guarantee for any of those architectures. So it's a quite open area to explore what kind of utility guarantee you can do for those more specific architectures. Thank you for your attention.
If anyone has questions online, they can put them in the chat. Or questions.
Question, comment. I think this is amazing work, by the way. This is great. But if I'm not an expert on this, but what I took of the limits is like, even when you do the dimensionality reduction, essentially you still need the dimension to be less than the logarithm of the number of examples. And that is one of those slides. It's like,
so
like
if you do the dimension induction, the D prime must be must be, so the intrinsic dimension still need to be small.
Yeah, but it's, go back to like slide 14.
Yeah, here. It still needs to be small. Yes.
Yeah, so I mean, it has to be pretty small. As I mean, I'm interested in practical applications for this. Like if you have to be less than logarithm examples, it's like you need like 1 million examples, 10 million, 100 million. You need 1 billion examples to have like 9 dimensions.
Yeah, yes.
And that's like
pretty
tough.
I already mentioned that there is critical difficult hardness result in computation, and in our like Wasserstein distance, this is like a statistical rate result. It's also a bit pessimistic. So in reality, if you manage to have a good utility of synthetic data, it must come from certain magic. Right? The magic is if your data is in an intrinsic low dimension, or the function you want to apply to the data is actually much better than like the worst one Lipschitz function.
Yeah, so I think
there are two directions.
Like
I make my function apply to the data very nice, smooth. Then we have a work in preparation, but I can tell you if the function is infinitely smooth. Lipschitz, you can think about like one derivative exists. Right? If my function is differentiable everywhere, all the derivative exists, then I don't have this factor. I have like 1 over n. Great.
Yeah, I mean, we've done some work on like with membership attacks on imaging, learning on imaging, and we added some noise, and you get some kind of Pareto function between the accuracy and the vulnerability. But it's not there's no guarantee.
This n to the minus 1 over d is essentially inherent in all this Wasserstein learning problem. If I want to learn a density function in d dimension, the samples you need to pay to get a small Wasserstein distance error is essentially exponential in d. So this is the limitation of this metric. So that's why my question is, how can we like move beyond the Wasserstein distance? The nice thing of Wasserstein distance is it makes our algorithm intuitive. Wasserstein distance is the average cost you remove points. So the algorithm built on this intuition that I'm removing points carefully, then I am calculating the loss in this Wasserstein distance by optimizing the point to move. Yeah, that's a good question. Thank you.
Thank you.
I
Okay.
think that one of the directions is more promising than the other. Like I guess you're doing something in preparation about easier.
Yeah, so I'm saying either there are 2 ways to make this rate better. Right? One is I assume I have some manifold hypothesis of my data, and that's the second question. And how do you make an efficient algorithm that's adapted to this manifold structure? This is still quite open.
Okay.
And I think the first question also quite open. How, if I give you a nice function class, can you create an algorithm that's adapted to this function class? The function class is infinite with many functions, but improve the rate. Yeah.
I think this is a discussion we're having before your talk, but I still kind of have this question. So, in this work, I assume there's some sort of like IID expectation over the points, but in relation.
Oh, not really. Our points are deterministic. So the IID functions are not noise. Yeah, that's a good observation. So we are taking expectation, right? Whenever we do the bound. So if you look at this expectation is over the Laplace noise.
Okay.
Yeah. So this is for any data set X in the hypercube. I can create a Y such that this rate holds.
But so I guess my question is, well, let's, when you're generating these synthetic data points, we're talking about the example of, well, a person's employer and their residents are co-located in the same city. So really, you might have these two pieces of information, the employer's, the person's employer, the employer's location, and the city in which the person resides. And now when you're generating a synthetic data point, really there's kind of a dependency on these other two synthetic data points that you would expect. And so how do you kind of capture that relational pattern in the generation of synthetic data?
Yes, okay, good question. I think I saw some work on this. You can model this relation as a graph.
Mhm.
And you want to create a synthetic data that keeps this graph structure.
Right.
And I think there are some work done on this. I can share some reference.
Yeah, I mean, I guess like what's the intersection of that kind
But
of?
this is not our structure. We're looking at tabular data essentially. Every point is a d-dimensional vector. But I think you have a graphical structure of your data, and you want to keep that. That's a mixed type, right? You have some value and a discrete structure.
Yeah, I mean, but
you
you can always turn the graph into a tabular discrete structure, right? Like you could have an indicator variable of the,
But it has way more structure than our distance. So
right.
We are just measuring the closeness of 2.5, the distance in the hypercube. That's not the distance you are.
Yeah.
Yes. Maybe a question on the utility side of the accuracy. So the whole premise here is that if you have close points, so close enough, you can they become distinguishable, but they don't hurt the ultimate performance of the learning algorithm or predictions or whatever. So what are the limits there? I mean, I can imagine in machine learning problems. Again, it comes back to the high dimensional thing. I mean, high dimensional objects, the distance between them is pretty tricky. So I mean, if they look very close, but maybe they do affect the classification performance. So how do you kind of capture the utility? I mean, I guess you're assuming that you're only changing like one at a time here. I'm trying to understand, I mean, the effects on the accuracy when you do the privacy guarantees. I mean, you showed some result on the effect on accuracy of the probably mechanism. But I think in general, I mean, if I have a real data set and begin to change points or to cluster points or represent a small cluster by a single point, how do you guarantee the final accuracy remains similar?
So yeah, you might have a bad situation is if, for example, you do classification and all the points are on the margin that on the boundary. That's your setting. If I perturb the point, they can lose the accuracy.
Well, I'm just trying to understand is like the premise here is that you're able to basically you make a data set basically private by essentially collapsing points in a small region close to nearby.
Yes.
But it's not obvious to me that by doing that, you may not affect the ultimate outcome of the algorithm by a lot, because maybe there are like small differences even if they're kind of close in the full Euclidean distance, they're still may classify differently.
If you have some loss that's like a 0-1 loss, then it's not work.
Yeah.
If your loss is Lipschitz, then if I change the location bits, I won't do that.
Yeah.
But
Okay.
there are limitations with this Wasserstein. But this is our first step, and we aim to make it more broad out.
If there are no other questions, I think we can wrap things up. But thank you again.
Thank you for your attention.
speaking with us.